Let me recall that we are discussing the transformations of the Dirac equation with respect to Lorentz group. We consider Lorentz transformations, and we finished the last lecture by understanding how our spinor transforms under parity transformations. Now I'm going to discuss the remaining type of transformations which we have not yet discussed, namely time reversal. So the theme is now time reversal. And we have to understand how our Dirac spinor transforms under transformations of the type t goes to minus t. Classically, having such a transformation or having such a symmetry means that all solutions, all trajectories, say q depending on t, all solutions of the equations of motion are time reversible. So in other words, if you pass from such a solution to another solution, to another function q ref on t, which is q on minus t, so you replace time for minus time, then this q rev on t also appears to be a solution of the equations of motion. And in this respect, you can say that this transformation, this discrete transformation t going to minus t, is in fact a symmetry of your equations. In our quantum mechanical situation of the Dirac equation, we have to continue with this time reversal symmetry absolutely in the same way as we have done, say, for instance, for parity. So we assume that time reversal symmetry is some operation. Let me denote it by this letter, which is probably calligraphic T, which is, I think, is kind of a calligraphic T. And this transformation is assumed to act on our spinor psi in the following way. So psi prime on x prime is given to is given to t, t calligraphic applied to psi on x, where x prime is an operation of time reversal, which in fact does not do anything to spatial coordinates, but transforms the time coordinate. So x prime on with zero component is minus x0, while x prime I is equal to xi. So this is special components of x, they are unchanged, and time component of x changes the sign. Now, given such transformation t, which you would like to associate with time reversal, you can first have a look what actually happens in quantum mechanics under time reversal. So without going even to a field theory, to the Dirac equation, first you might ask how this operator actually acts in usual quantum mechanics. And in quantum mechanics, transformations of operators under symmetries is done in the following way. So if you have some operator A, then it transforms as, say, under action of this T as T A T minus 1. So that's what gives a transformed operator. And in quantum mechanics, we then have to assume that if we have an operator of coordinate, then this operator is not does not change under this transformation. So T acting on X, T minus 1, gives you simply x. So coordinates of a particle do not change. But in addition to operator of coordinate, we have also an operator of momentum. And since momentum, through its definition, involves the time, so momentum p, even classically, you understand that this is dx over dt multiplied by mass, say in non-relativistic quantum mechanics, then since it involves time, under such an operation, p in quantum mechanics, operator of momentum, must change the sign. So p goes to minus p. And on the other hand, if you look at the fundamental commutation relation of quantum mechanics, that operators pi, commutate of operators pi with operators xj gives you I h bar delta ij, so Heisenberg commutation relation, then this commutation relation will be invariant under such a transformation with t, if and only if this operation t acts also on imaginary unit in the following way. So when it passes through imaginary unit, it gives minus I multiplied by minus. Well, you see it from this relation here. So if you apply to it t pi xj, t minus 1, then on the left-hand side, you will get pi transformed, xj transformed. And as we said, p will change the sign. X is not changing sign, so you will get pi xj. And on the right-hand side, well, you have now to see what happens. On the right-hand side, you will get minus pi xj equals to imaginary unit multiply from the left by t and from the right by t minus 1, h bar delta ij. From where you see that to reproduce this minus sign, the action on imaginary unit must be actually non-trivial and satisfy this relation here. So this means that in quantum mechanics, Hamiltonian is invariant, well, in quantum mechanics, Hamiltonian is invariant under time reversal, and for Heisenberg equations to be invariant with respect to time reversal, this time reversal operation should act non-trivially on I. And in general, such a transformation is realized by the so-called antilinear, anti-unitary operators. So T is realized in quantum mechanics, by the so-called antilinear, anti-unitary transformations. Antilinear transformation is clear from the definition of what linear transformation is. And now linear transformation would be if you have a wave function and you psi and you multiply it with a complex number lambda, and then you apply t, then usual linear transformation would mean, if t is usual linear transformation, it would mean that you can take lambda out and you would get just t applied to psi. But antilinearity means that actually when such an operator passes through a complex number, the complex number gets conjugated. And anti-unitarity means something else. The notion of unitarity is defined with respect a chosen scalar product in your space, in your Hilbert space. And anti-unitarity means that if you have a scalar product and you have two elements of your space, so x and y, and you apply this operator T to x and y and compute the scalar product, then the result of this transformation, for unitary transformation, you will just get back the scalar product x with y, but for anti-unitary transformation, you get xy conjugate, which, according to the definition of a scalar product in quantum mechanics, is y with x. And so you see time reversal already in quantum mechanics is different from what you normally think about transformations, about symmetries in quantum mechanics, in a sense that symmetries are realized by unitary operators. Concerning time reversal, as you see, this is not the case. And the time reversal is realized by antilinear, anti-unitary transformations. And of course, this feature of quantum mechanics then goes to the quantum field theory. So we are not surprised that the operator which we will be finding also in the Dirac theory, which corresponds to this time reversal, also has a property of similar types. And we therefore assume the following, that our transformation from psi on x to psi prime on x prime, which is transformation with this operation t acting on psi on x, can be explicitly realized in the following way. It is, first of all, involves a complex conjugation. So from a spinor psi, you come to a complex conjugate spinor. And then this is not yet the end of the story, because our equation is a matrix equation. And we have to admit the possible multiplication of this conjugate spinor psi with some matrix T, which for T, we assume that T is a normal unitary matrix, is a unitary matrix, is a unitary matrix. So this operation T is therefore kind of twofold. It involves multiplication with a usual unitary matrix, which would be a normal thing, but it also involves an operation of complex conjugation of the original function psi. And this conjugation is responsible, in fact, for the feature that such a transformation will be antilinear. Now, to find what is actually this matrix T should be, we take our Dirac equation and we, as before, assume that in the transformed Lorentz frame, transformed by means of time reversal, the Dirac equation should look the same as in the original frame. So in other words, there should be the usual Dirac operator, but with x replaced by x prime, acting on psi prime on x prime, should give us 0. So that's our standard way of implementing what we call the Lorentz covariance of the Dirac equation. Now, we start from this equation. Well, actually, we can, what we can do, we can start from the usual Dirac equation and try to bring it to this form above by means of complex conjugation and multiplication with the matrix T, as I'm claiming here. So what we first do, we take this equation as a whole and complex conjugate it. So when we complex conjugate, we get minus I say gamma 0 star. Let's conjugate matrix gamma 0. And then we have d over dx 0. X0 is a real variable, and therefore it remains invariant under complex conjugation. Then there is minus I gamma I complex conjugate. Minus now, minus is just there. Then there is, I mean, complex conjugation is, we keep it here on gamma I, and then there is d over dxi minus mc divided by h bar, and all this is multiplied by psi star on x is equal to 0. Right, so minuses again come here because of I. And now the only thing I have to do, I have to rewrite this gamma 0 via minus gamma 0. So I will just take plus here, and instead of gamma 0, I will write gamma 0 prime. Xi is equal to x prime, so I can just straightforwardly put on x prime. And the final thing which I will do, I will multiply this equation from the left by t. And so then the equation will have the following form. So if I multiply it by t, I will get I t gamma 0 star. Here I will write t minus 1 t, and t I will then put close to psi star, like this. D over dx prime 0 minus I t gamma I star t minus 1 d over dx prime I minus mc over h bar. That is how equation looks like when we multiply it. Multiply from the left. From the left with t. Multiply it from the left with the matrix t. Now, we have almost done. So this, the form which we have to compare to this equation here. So these two we have to compare. This is psi prime on x prime. This is what we want. And in order to, for this equation to coincide with this expression here, what we have to do is to require that t gamma 0 star t minus 1 is gamma 0, and t gamma I star t minus 1 coincides with minus gamma I. Then our conjugated and multiply with t equation will just turn into the Dirac equation in the new frame. So this means that matrix T must satisfy these relations here. And now to solve these relations for a matrix T, we have to specify, of course, the representation for gamma 0 and gamma i's, because we need to know, we need to explicitly realize how the conjugation acts on these matrices. And say if you pick up Dirac representation for gamma matrices, then we know that gamma 0 is real. So gamma 0 star is gamma 0. Gamma 2 star is minus gamma 2. That's because gamma 2 is constructed with the help of the Pauli matrix sigma 2. At matrix sigma 2, you remember, it's of diagonal matrix containing I and minus I. So the under complex conjugation, this matrix, this Pauli matrix, change the sign, and therefore gamma 2 will change the sign. And the matrices gamma 1 and gamma 2, they are real because they are constructed with the help of Pauli matrices. Gamma 1 and gamma 3 are real because they are constructed with the help of Pauli matrices sigma 1 and sigma 3, which are real matrices. Therefore, eventually you see that what we have here is T gamma 0, T minus 1 is gamma 0. T gamma 2, T minus 1 is gamma 2. And T gamma 1, T minus 1 is minus gamma 1. And finally, T gamma 3, T minus 1 is minus gamma 3. Okay, so this is conditions for this matrix T we have to satisfy. Well, you can actually easily see what should be a solution. If you take T to be proportional to the product gamma 1, gamma 3, then you have done. That's because gamma 0 anticommutes with gamma 1 and it anticommutes with gamma 3. Therefore, when you will be taking gamma 1, gamma 3 through gamma 0, you will get gamma 0. Because any such relation can be actually rewritten as the commutation relation. Gamma 0 is equal to T. If you multiply it from the right by T, then you see that this is what you have to satisfy. So in other words, matrix T must commute with gamma 0, it must commute with gamma 2, but it should anticommute with gamma 1, and it should anticommute with gamma 3. And that's exactly what this product gamma 1, gamma 3 does. It anticommutes with gamma 1 because gamma 1 commutes with gamma 1, but gamma 1 anticommutes with gamma 3. Therefore, there will be minus sign appearing as a result of commutation. And the same is with gamma 3. Gamma 3 commutes with gamma 3, but gamma 3 does not commute with gamma 1. And again, there will be minus sign. While, as I said, gamma 1 and gamma 3, they are both anticommuting with gamma 0. So sign changes twice, and therefore, as a result, T will commute with gamma 0, and the same is with gamma 2. Well, in principle, T is defined up to an arbitrary phase, and very often people just fix this phase, take a convenient choice, and usually they pick up here I. So T is then explicitly realized as I gamma 1, gamma 3. And this means that we have built up the action of the time reversal operation on our spinor, and it looks like this T operation applied to psi on X, and explicitly this is I gamma 1, gamma 3, psi star acting on X. This is how this transformation looks like. So this operation is known in general and in this particular case as a Wigner time reversal operation. So this is Wigner time reversal operation. And it is represented, as I said, by antilinear, anti-unitary operator, which you can explicitly realize as multiplication with the matrix T, and then an operator of complex conjugation. So here K, I may think about it as being an operator of complex conjugation. So when such an operator is applied, say, to our spin up psi on X, what it does, it just complex conjugated. So in this respect, you can see that this is exactly the realization of an operator of the type which I described as anti-linear and anti-unitary operator. Now, you can also, if you wish, you can also alternatively describe or alternatively derive the same result about the form of time reversal operator just by requiring that Dirac-Hamiltonian is invariant with respect to this operation of time reversal. You will come to the same result, essentially to the same result for the form of this operator. Okay, that is what concerns time reversal. Yes?
Can we say that tau here is the time reversal for the complex conjugate or like antiparticle? What do you say?
Once again, antiparticles I will discuss soon. So we come to the antiparticles. Passing to antiparticles will also involve the operation of complex conjugation, but this will be different from what I'm describing here. From the time reversal, so in other words, time reversal and the transformation which transforms particle to antiparticle, they both involve complex conjugation, but they are different. They are different symmetries of the Dirac equation. Okay.
So what does tau here means physically?
That's exactly what I said. The Dirac equation is covariant under the operation of time reversal. You change the time t to minus t, and in the new Lorentz frame, Dirac equation will look the same. Covariance of the Dirac equation under time reversal. So time reversal is Lorentz transformation, is a particular Lorentz transformation.
Okay.
So it's a particular Lorentz transformation. Yes, it's a discrete Lorentz transformation, but it's a Lorentz transformation. So this means that since we adopt the relativity principle that all laws of physics should look the same in any Lorentz frame, this means that if we take our Dirac equation and transform it to a new Lorentz frame where time transforms to minus time, then the Dirac equation in the new frame should look the same. And the question is then how psi should transform in order for the Dirac equation to fulfill this property, to look the same in the transformed frame. And the answer is exactly what I'm writing here. Then what you have to do, you have to transform your psi in the following way. You have to complex conjugate it, and you have to multiply it with the matrix I, gamma 1, gamma 3. So in this way, you guarantee that your new psi will satisfy the same Dirac equation in the new frame. And the physics principles will be preserved.
Yeah, okay. Understood.
Okay.
Thank you. Yep.
But to antiparticles we will come. So now I would like to introduce another important class of spinors and clarify more the question about reducibility of the proper orthochronous Lorentz transformations. And so this subject, which I'm going to discuss now, is the subject about Weyl spinors. Weyl spinors. So in the last two lectures, what we have done, we have constructed a representation of the proper orthochronous Lorentz group on our four-component spinors. And this representation is realized in terms of 4x4 matrices. And these matrices I denoted by letter S, and they depend on the Lorentz transformation, which we perform on the space-time points, on the space-time vectors. And we have seen that this S on R realizes what we call spinor representation of the Lorentz group. Very interestingly, it turns out that this representation, which we have constructed, is reducible. This representation turns out to be reducible. And what does it mean that this representation is reducible? So to understand this, you have to give a definition, what you call by irreducible or reducible representation, how you distinguish reducible from irreducible representations. So there are two definitions of what you can call irreducible representation, and these definitions are equivalent. So the definition number one says that representation of a Lie group, which in our case is of course Lorentz group, is irreducible if there are no invariant subspaces. If this representation has no proper invariant subspaces. Proper means subspaces which are different from zero and the space representation space itself. That's what it means, proper. Because you always have invariant subspaces, which is just a zero space and the space itself. This we exclude. And if we exclude this, then this definition of irreducibility means that if our representation is irreducible, then no other invariant subspaces exist. So in other words, if you start from any vector in your representation space, then by group transformations, you will reach any other vector in your space, and it does not happen such a situation that there will be a subspace in your representation space whose elements transform, whose vectors transform via themselves and never get out of this subspace. That's what it means, irreducibility. Let me ask if this concept is clear.
It's clear, Professor.
Yes, yes.
Okay, so no invariant subspaces, very simple. And the second definition is telling you that representations of a Lie group, a representation of a Lie group is irreducible. So representation again of a Lie group is irreducible if the only operators which commute with all group elements, are only those which are proportional to the identity operator. That are proportional to the identity operator. In other words, these operators which commute with any group any group elements are operators of the form constant multiplied with identity operator, and no any other non-trivial operators except this one exist. So if I represent, say, the action of the group element in your representation space as P depending on the group element G, so it's like a matrix acting on a concrete representation space, then irreducibility means that there is no any non-trivial operator like O such that it commutes with P on G for any group element G, and O is not equal to C multiplied by identity, because C multiplied by identity always, of course, commute with any P on G, but if you exclude those, then there should not be any such O. No such non-trivial O should exist. No such O should exist. So this is another definition of what you can call irreducible representation. And in fact, in representation theory, you prove a theorem that definition number 1 and definition number 2, they are equivalent. So this is the same to say that your representation is irreducible if there is no an invariant subspace, any invariant, proper invariant subspace, or the same as to say that representation is irreducible if the only operators which commute with all group elements are those which are proportional to the identity operator. That's the one and the same thing. Let me not to prove this theorem, just, I mean, as a brief indication, let me say that you see that if there is an invariant subspace, then there is also a projector on this invariant subspace, and you can construct a non-trivial projector operator, which projects on this invariant subspace. But then, because it is invariant, you can see that this projector is exactly this non-trivial operator, which does appear, and then which is an operator which breaks the irreducibility from the point of view of second definition, and essentially vice versa. So it is then clear, more or less, how this proof should go. You rely on the fact that actually you can build up then projection on this representation space, and it gives you this non-trivial operator which breaks irreducibility. Now, so if we look from the point of view of the second definition on the representation which we have constructed, and ask ourselves why we think that a representation that we have constructed as on R, acting on our Spinors representation of the proper Arsachoros Lorentz group, why this representation is reducible, then we say, yes, it is reducible if we find a non-trivial operator which does commute with all group elements. So with all S on R representing elements of the proper Arsachoros Lorentz group. And so my statement is that, yes, indeed, such an operator, non-trivial operator, does exist. And it's actually very easy to see that this operator is simply multiplication with matrix gamma 5, because gamma 5 is a matrix which commutes with all proper Arsachoros Lorentz transformations. You can see that the result of this is actually 0. And why is the reason? What is the reason for that? That's because we know that this S on R are realized explicitly as exponent 1/4 gamma mu gamma nu omega mu nu, where this gamma mu are our Dirac matrices. So mu is running 0, 1, 2, and 3. And then gamma 5 is a matrix which has a property that it anti-commutes with all matrices gamma mu. So anti-commutator of gamma 5 with gamma mu is equal to 0. So it anti-commutes with all of them. But if it anti-commutes with all of them, then in fact it commutes with the product of any two such gamma matrices, because it anticommutes with the first. It gives you have minus sign, then it anticommutes with the second. You give another minus sign, and as a result, it simply anticommutes. So you can see it in the following way. Maybe more explicitly, you write it like gamma 5 exponential 1/4 gamma nu, like this. Then you can use the fact that gamma 5 squared is equal to 1. So you can write here gamma 5 like this. And then you use the fact that this can be rewritten as 1/2 gamma 5 gamma mu gamma nu gamma 5 and omega mu, I forgot, sorry, omega mu here, gamma 5. And then you move gamma 5 through gamma mu, and then it cancels, and here then you get a Lorentz transformation back multiplied with gamma 5. Multiplied with gamma 5. Oops, multiplied with gamma 5. Okay, so this is how it works. Yes, indeed, I show you non-trivial matrix gamma 5, which you can think of as an operator acting in this four-dimensional representation of the Lorentz group, and it commutes with all S on R, representing Lorentz transformations. Okay. Any questions? Is this clear or?
But does gamma 5 also Lorentz transformation or representation of Lorentz transformation?
Sorry, say it again. Yeah.
But what is gamma 5? It is also some corresponding to some Lorentz transformation. I mean,
No,
is it
no. Gamma 5 we have constructed in an explicit way by saying that gamma 5 is built up. So that's the definition of gamma 5. Let me repeat it. Gamma 5 is I, gamma 0, gamma 1, gamma 2, gamma 3. So it's a product of all these gamma matrices. Gamma 5 does not take part in Lorentz transformations. I mean, in a sense, Lorentz transformations S on R, they are explicitly, all of them, transformations which correspond to a proper orthochronous Lorentz transformations. These matrices S on R have an explicit form like this. Remember, yeah? That's what we have constructed. This S on R act on our spinors and gives the spinors in the transformed Lorentz frame. Okay?
okay?
And now gamma 5 is what it is. It's just a product, essentially a product up to this I. It's a product of the four gamma matrices, and I is added here to guarantee the properties that gamma 5 taken in square gives you 1. Gives you identity matrix. Now, but gamma 5, of course, acts on spinor. So if you have a spinor psi on X, you can multiply it with the matrix gamma 5, and then you get another spinor. And so what I'm saying is that now, explicitly what I'm saying is the following. So I'm saying take a spinor psi on X, take your spinor psi depending on X, take your spinor psi depending on X, multiply it with matrix gamma 5, and then apply a Lorentz transformation. And then the result will be the same as to take your spinor psi on X, first apply a Lorentz transformation, and then multiply with the matrix gamma 5. The result on the left will be the same as the result on the right, as a consequence of the fact that gamma 5 does commute with all S on R. And therefore, according to the logic of our definition of irreducibility, the representation of the proper orthochronous Lorentz group is reducible. And the matrix gamma 5 exactly helps you then to construct invariant subspaces, subspaces which remain invariant under proper orthochronous Lorentz transformations. This is done by means of constructing explicitly two, as people say, chiral projectors, P plus minus, which are given by 1/2 identity matrix plus minus gamma 5. Plus minus matrix gamma 5. This P plus minus, they have the property of being projectors, indeed. So this means that P plus minus taken square, you get P plus minus. So this is exactly the property of the projector. When you square it, you get this operator back. This is property number 1. Property number 2 is that these projectors P plus P minus, they are orthogonal. So if you multiply P plus with P minus, or P minus with plus, you will get 0. And the third property is that actually these projectors realize the decomposition of identity. So if you add them up, you will return back to the identity. But this is clear from the definition immediately. When you add them up, then gamma 5 cancels out because of this plus minus signs. And then twice 1/2 of 1 gives you identity matrix. So this property is clear. The other properties follow immediately from the properties of gamma 5. Say, for instance, if you take, say, P plus and multiply it with P plus, so you will get 1/4, 1 plus gamma 5, 1 plus gamma 5. And then you open up, so you get 1/4, 1 plus twice gamma 5, plus gamma 5 squared, but gamma 5 squared is 1. By 1, I mean identity matrix here. So you get 2 gets out, and then you get 1/2, 1 plus gamma 5, so P plus back, you see? That's the one thing. And if you take P plus P minus, you get 1/4, 1 plus gamma 5, 1 minus gamma 5. And then this is 1/4, 1 minus gamma 5 squared, but gamma 5 squared is 1, and so you get 0. So projectors are orthogonal. They are projectors, yes, and these projectors are orthogonal, and moreover, they provide a decomposition of the identity. So this means also that, I mean, from the explicit expression and the properties that gamma 5 commutes with Lorentz transformation, proper synchronous Lorentz transformations, it follows from here that P plus minus also commute with all proper orthochronous Lorentz transformations. Also commute with all proper orthochronous Lorentz transformations. Okay, so this means that actually we can define objects which explicitly realize these invariant subspaces. And these objects are spinors, they are special spinors, which are called Weyl Spinors. So a Weyl spinor, then a Weyl spinor, is defined as a two-component spinor, not four-component, but a two-component complex spinor. No, complex means that these two components are complex numbers. Two-component complex spinor, which transforms irreducibly irreducibly under proper orthochronous Lorentz transformations, and we know that those form a group with a name SO plus 1,3. So in other words, our four-component Dirac-Spinor realizes a reducible representation of the of the proper orthochronous Lorentz group, but I can split it into two-component spinors, and each of these two-component spinors will realize now irreducible representation of proper orthochronous Lorentz group. So explicitly, these two-component spinors are constructed from our four-component Dirac-Spinor by applying the projection P plus to psi and the projection P minus to psi. So P minus acting on psi. So here psi is four-component Dirac spinor, and this will be essentially two-component Weyl spinor. Of course, it will have four components, but only two components will be independent. Now, in fact, these spinors psi plus and psi minus are called chiral, and people say that psi plus and psi minus have different chirality. Maybe to understand more why how these two-component spinors look like and why I'm saying that they are actually two-component, what you can do is to pass from a Dirac representation of the Clifford algebra, which explicitly is given by gamma matrices of the form gamma 0, 1, 0, 0, minus 1. You remember this form. Gamma I is 0, sigma I minus sigma I 0, to another representation, the so-called pass to the so-called Weyl representation. Where these matrices are realized in the following way. Gamma 0 is taken to be off diagonal, and gamma I remains to be the same, like this. Now, you can see that if you compare this to explicit matrix gamma 5, you see that in fact, if you denote the matrices of this representation with the letter C, means chiral, then you see that gamma 0 in the chiral representation is nothing else as gamma 5 in the Dirac representation. And gamma 5, which you can construct through these chiral matrices in the chiral representation, is minus gamma 0 in the Dirac representation. So essentially what happens is that when you come to the chiral representation, gamma 0 and gamma 5 change the role. Gamma 0 becomes gamma 5 and gamma 5 becomes gamma 0. As we said, all representations of the Clifford algebra in 4 dimensions are related to each other by means of unitary transformation. Therefore, there should be a unitary transformation which relates these two explicit realizations of Clifford algebra. And indeed, you can see that there is a matrix U which does this job. So when you apply it to all matrices gamma of the Dirac representation, you will obtain matrices of the Clifford, or you obtain the gamma matrices of the Weyl representation, and explicitly this matrix U is given by identity for 2 by 2 identity minus 2 by 2 identity here, identity. So it looks like this. No, and then I need to add up some overall constant, which guarantees that the matrix which I have constructed is actually unitary. Indeed, you can just perform a unitary transformation with this matrix U of matrices in the Dirac representation, and that again these matrices in the Weyl representation. But what is good about these new gamma matrices is that now if you write your spinor explicitly, we are two-component spinors, so like phi and chi, where each of these phi and chi is two-component, then you see the following. That first of all, we have already seen that under orthogonal transformations, the matrix S, let me write it down. Let remind you that the matrix we have constructed corresponding to rotations was already factorized. It was 1 cosine theta over 2 plus I sigma n sine theta over 2. Here there was 0, 0, and then 1 cosine theta over 2 plus I sigma n sine theta over 2. And this matrix is already factorized, and it shows that under rotations, phi and chi transform independently. They do not mix. They do not mix under rotations. This matrix S we have constructed from the general formula, exponential 1 over 4, by specifying here the indices of gamma matrices to 1, 2, 3. So these matrices do not involve gamma 0. This construction does not involve gamma 0. But since passing from Dirac basis to Weyl basis of gamma matrices, there is no change of gamma i's, then this result for S on n theta for Lorentz transformations corresponding to rotations will hold also in the Weyl representation. So the result will be the same. So phi and psi will transform independently and do not mix. They continue not to mix. Now, if you go to Lorentz transformations, if you go to Lorentz boosts, so we have seen that in the case of the Dirac representation, phi and chi do mix. But now you can ask yourself what happens in the new basis, because here your matrix gamma 0 in the Weyl basis, in the Weyl representation, is off diagonal. And Lorentz transformations corresponding to Lorentz boosts, they have the form 1 over 4 gamma 0 gamma I omega 0 I, probably with the coefficient 1 over 2 here. But now you see the following, that gamma 0 is off diagonal and gamma i's are off diagonal. And if you multiply two such off diagonal matrices, you get a diagonal matrix, right? Before, the difference was that gamma 0 was diagonal and gamma I was anti-diagonal, or off diagonal as we call it. And so the product of gamma 0, gamma I, in first case, gamma 0, gamma I, will be off diagonal. But here it becomes diagonal. Gamma 0, gamma I is diagonal. But if it is diagonal, then you see that the matrix corresponding to Lorentz boosts will be diagonal as well. And so you can compute it explicitly. S on n and hyperbolic angle var theta. And you find that it will have the following form. 1 cos hyperbolic angle var theta minus sigma n sinh var theta over 2, 0, 0, as I claimed, 1 cos var theta over 2 plus sigma n sinh var theta over 2.
This is for the Weyl representation, right?
This is for the Weyl. So this is the same as for Weyl and Dirac. Weyl and Dirac. So this is the same. And this is only for Weyl. And so you see that, what does it mean? What is the meaning of this? Is that actually phi and chi do not mix under any proper orthochronous Lorentz transformations, neither under rotations nor under Lorentz boosts, because the corresponding matrices we compute in the Weyl representation, you see, they are just block diagonal. They are just block diagonal. That, of course, shows that indeed phi and chi are our Weyl spinors. So phi and chi are Weyl spinors. I meant that these are two-component spinors. You see that they are two-component Weyl spinors. And indeed, they transform independently under proper orthochronous Lorentz transformations. The other important remark is the following. You see that the difference between phi and chi is also visible from these formulas. The difference is that under rotations, phi and chi transform completely in the same manner. These transformation matrices are actually equal. You see, they are the same. They are the same. They are the same. This is not the case for Lorentz boosts. For Lorentz boosts, one of these matrix, I mean, phi transforms here with the matrix, upper matrix, which has minus in between two terms, while chi transforms with a matrix that has plus sign in between these two terms. So these transformations for phi and chi with respect to Lorentz boosts look different, and the difference is this sign. And yeah,
if I'm not wrong, why we use Weyl representation for the case when the particle's energy is very high, right?
No, it has nothing to do with energy. Why you say so?
Because you have two different spinors. So for the standard representation, I think it's a normal case, but it seemed to me so.
No. This is pure what I'm discussing. A priori has nothing to do with energy. No. What I'm saying is that this fact, which I'm trying now to convey, is purely about representation theory. It's a purely group theoretic fact. It's about group theory. Once again, I'm saying the following, that you have a Lorentz group. So Lorentz group is, let me denote it topologically like some set of transformations. Within this set, there is a smaller subset, which we call a subgroup of proper orthochronous Lorentz transformations. And this subset, we use for it a name as O plus 1, 3, and we call it proper orthochronous Lorentz group. Now, we established transformations of our spinor psi our spinor psi on x with respect to SO plus 1, 3. And when we have done this, we realized that this representation of SO plus 1, 3 on 4-dimensional spinors, on 4-component spinors, those which have 4 components, because 4 components are needed for the Dirac equation. This representation was SO plus 1, 3 on 4-component spinors turns out to be reducible. And it splits into 2 invariant subspaces in the following way. So psi is phi and chi. And this split is very explicitly is realized if you just pass to a particular nice representation of the Dirac gamma matrices. All representations of Dirac gamma matrices are equivalent. You can use any of them. Their fact about reducibility does not depend on which representation for gamma matrices you pick up. The Weyl representation has only one nice thing, is that in this representation, the split into 2-component Weyl spinors becomes truly obvious, becomes very much visible because you can say that you associate with Weyl spinors 2 first components, 2 upper components of the spinor psi, and with another Weyl spinor, you associate 2 components, bottom components of the same spinor psi. So in Weyl representation, these are just these 2 components here and these 2 components here. These are just Weyl spinors, which now transform irreducibly under SO plus 1, 3. You can also see that the split into 2-component spinors will persist in any other representation of Dirac gamma matrices. In the original Dirac representation, it is also there. It might look more complicated. For instance, in the 4-component psi, you might identify psi 1 with psi 4 and psi say 2 with psi 3, like this, or in a more complicated way. You see, but in the Weyl representation, this split becomes obvious. Because then the upper 2 components is one Weyl spinor, the other 2 components are the other Weyl spinor.
Because like they transform differently.
Yes, you see that they transform in the same way under rotations. Matrix which transforming phi and transforming chi coincide, while under Lorentz boosts, this is not the case. Because in one case you have minus, and in the other case you have plus. Now, this is not the end of the story about this, because you may still ask the following question. So, okay, so these guys transform with different matrices realizing Lorentz boosts, but maybe these representations are still what is called equivalent. And 2 representations are called equivalent. Representations are equivalent if there exists a unitary transformation such that if you take, say, matrices of the first representation, say P on G, and you transform them with this unitary transformation, then you get the matrices of the second representation. So this is first representation, and this is the second rep. first rep and the second representation. So such representations which are connected by unitary transformation, they are called equivalent. No, because in this case, equivalence is just a statement that you get one representation from the other by changing the basis with the help of the unitary transformation. You change the basis by means of this matrix U, and your first representation gets into the second. So it's trivial. It's trivial. So it's trivial connection between the representations. And in fact, in representation theory, people agree to consider unitary representations of Lie groups up to unitary equivalence, which makes a lot of sense, because why should I consider as different representations two representations which are different just by the choice of basis in representation space? Basis you can always change if you wish. Okay, so the question here which you might ask is the following. Okay, in spite of the fact that you have here different signs, maybe your representations are still equivalent, and maybe changing the basis in the representation space, say of spinor chi, you will get a representation of spinor for a spinor phi, and in this case these two representations will be equivalent. The answer to this question is negative. No, these representations are not equivalent. These are really, really different representations. And to see that they are not equivalent, you can say, well, suppose they are equivalent, then it means that there should exist a matrix U such that it takes a matrix of the, say, first representation, 1 cos theta over 2 minus say sigma I. No, let me write it down like this: sigma I and I sinh var theta over 2 and U minus 1, and takes out of it the matrix of the second representation, var theta over 2 plus sigma I and I sinh var theta over 2. And this should be valid. This should be valid for any var theta and any n. So the question is, if such a matrix exists which does this for any var theta and any n, there should exist one matrix U which changes the sign in between the two terms. If such matrix does exist, then these representations of Lorentz group acting on phi and chi would be equivalent. Now, if you say that this should be valid for any var chi and var theta and n, you can pick up n whatever you like. So, for instance, you can take it of the form 1, 0, 0, or 0, 1, 0, or 0, 0, 1. So in all these cases, you will just get then three equations. Each of these is one equation, and so you get three equations where now instead of sigma I and I summed up, you will get just individual sigma I standing. So your equations now will split into three equations. Cos var theta over 2 plus sigma I sinh var theta over 2. Yeah, so this is what you get. And since also the choice, I mean, this term then is not important because here is identity matrix, and U and U minus 1 will cancel. So this term is exactly the same as this one. So these terms cancel. And then you see, then you can cancel, you can just cancel, you can just cancel this sinh sinh var theta on the left and on the right. And then your equation will be taken the form u sigma I u minus 1. And because of this minus, you can write it as minus sigma I. So this is an equation which you must satisfy in this case, from where you see that u should have the property u sigma I gives you minus sigma I u. So in other words, if such a matrix U does exist, it must be 2 by 2 matrix, which anti-commutes with all three Pauli matrices. I here is 1, 2, 3. Yeah, so if such a matrix exists, then it must anti-commute with all three Pauli matrices. But such a matrix which anti-commutes with three Pauli matrices simply does not exist. We don't know any matrix which anti-commutes with three Pauli matrices. You can easily make an exercise trying to construct it, but you will fail because there is no such U. No such U exists. No such U exists. So this means that these two representations of the proper orthochronous group acting on spinors phi and chi are inequivalent. They're really, really different. There is no unitary transformation which relates one to the other. And therefore, these two representations of spin 1/2, people agreed to denote them differently. So representation for phi is denoted as 1/2, 0, and the representation realized by chi is called 0, 1, 2. And the first spinors realizing this representation, I denote them phi. In general, this is a two-component spinor with index, would be two-component spinor with index alpha. And the other is also a two-component spinor with index alpha, where alpha takes values 1 and 2, but I have somehow to distinguish them on writing. And people agreed, say, to denote spinors of the type 1/2, 0 by putting dot on alpha, by putting extra dot. So alpha dot is 1, 2, and here alpha is taking values 1 and 2. It's taking values 1 and 2. So these spinors are called dotted, and these spinors called undotted. Yeah.
So here it's mathematical that we don't have any matrices that anti-commutes with Pauli matrices in this case.
Yeah.
So so in physically means that that phi and chi should be independent, right? They should behave independently.
This means that they behave independently in the sense that they transform differently under Lorentz boosts. Differently. And you cannot make a change of the basis in representation space such that they start transforming the same way. This is not possible. That's what it tells you. These are really different representations. By the change of the basis, you cannot make them transform in the same way under Lorentz boosts. Impossible.
Right. Yeah, according to symmetry, but like if you think of a particle, it is connected with a negative. Okay, so I will discuss this after I discuss antiparticle.
Yeah. So these two spinors, these two Weyl spinors, realize simply different representations of the Lorentz group. And now, if you come to the our early lectures where we discussed the construction of the Lorentz group, you remember I have mentioned there the following mathematical statement, that in fact the proper orthochronous Lorentz group, which is SO plus 1, 3, is not simply connected. It looks like a circle topologically, like this. But it has a simply connected cover. So you can cover it by another group, which is simply connected. And the name of this group is SL2C. SL2C. SO plus 1, 3 and SL2C, they have the same Lie algebra. They are both groups, they are both Lie groups, and they have the same Lie algebra. No, the same, it means Lie algebras are isomorphic, but these are not isomorphic as groups, and one is the universal cover of the other. In fact, SL2C is a double cover, which covers twice the group SO plus 1, 3. And in fact, you see, this is SL2C. So SL2C are 2 by 2 complex matrices. And what we are discussing here, this spinors psi alpha and psi alpha dot, they realize two inequivalent two-dimensional representations of SL2C. Psi alpha dot and psi alpha realize two inequivalent representations of SL2C. They realize two inequivalent representations of SL2C. And in fact, this is a kind of a general statement. So in general, this is a statement, in general, irreducible representations of proper Lorentz group, of a proper orthochronous Lorentz group proper orthochronous Lorentz group are characterized by two numbers, by two half-integer numbers. J1, J2. And so in one case, representation, say psi alpha dot, is a representation which corresponds to the choice J1 to be 1/2 and J2 to be 0, while the undotted spinor is characterized by choice of 0 and 1/2 for these half-integer numbers. And you see, you can now draw an analogy with the usual rotation group. For the rotation group, you know that representations are irreducible representations are uniquely characterized by just one half-integer number. And this half-integer number you call spin. So representations of rotation groups, that means representations of SO3, whose universal cover is SU2. So maybe I have to write it in this way. So let's write here SO3, and here we will write SU2, which covers it. And then representations are characterized by a unique number, half-integer number J, which you call spin. Yeah, so spin 0, spin 1/2, spin 1, spin 3/2, and so on. If you make an analogy with Lorentz group, then you see that Lorentz group extends, of course, SO3, to SL2C. Sorry. It extends it to SO plus. Let's write it in this way. So this is SO plus 1,3 here. And it's covered by SL2C. So SL2C is a cover, double cover of SO plus 1,3. And representations of those are characterized by two spins, J1 and J2. So Lorentz group is a bigger group, and its representations are actually more rich than those of the representations of just rotation group. And instead of one number, they are characterized by two numbers. And on the example of a Dirac spinor, an example of the Weyl spinors, we exactly trace here this statement. Now, from the point of view either of rotation group or of the group SO plus 1,3, these representations we are constructing looks like multi-valued representation. And we have discussed this. It's related to the fact that when you rotate by 2 pi, your spinor actually is not returning to itself, but it changes the sign. From the point of view of universal covers, here SU2 and SL2C, there is nothing strange happens. And in both cases, you deal with just two-dimensional spinors, which are usual two-dimensional objects transforming by multiplying with the 2x2 complex matrices. So nothing strange at all happens to them from the point of view of representation of the universal cover and the usual single-valued representations of the covers. This is how this construction of representation theory works. Okay, so what we have learned today, it's a very important fact, that the representation of the proper synchronous Lorentz group is reducible. And it splits into irreducible components, which can be conveniently described in terms of the Weyl spinors by choosing a Weyl representation for Dirac matrices. And in general, we observe a phenomenon that representations of the proper synchronous Lorentz group are described by two half-integer numbers, which is different from similar construction of irreducible representations of rotation group, which is described by just a single half-integer number. Another remark is the following. Of course, you can come back to this picture, which I draw here, and say the following. Okay, so we understood that this representation of SO plus 1,3 is reducible. And we can reduce ourselves to Weyl spinors, which form irreducible representation of SO plus 1,3. But what about this red, in other words, full Lorentz group, which includes all the other elements which can be obtained from SO plus 1,3 by applying parity and by applying time reversal operation. So for instance, you can ask yourself, so what about parity? Is it still phi and psi transform independently under parity? And the answer is no, no. Actually, if you look at our parity operation, which we have discussed last time, we found out that the parity operation is realized by means of, so what is parity? Parity was, just a second, let me take black. So parity is realized essentially up to this eta p by the matrix gamma 0 acting on psi. And in the Dirac representation, in Dirac, psi 0 was diagonal. So it was eta p here 1, 0, 0, minus 1 psi. And so if I write psi as phi and chi, you see then this is EP phi minus eta p psi, like this. So in principle, in the Dirac representation, you see that they do not mix. However, when you pass to the Weyl representation, to guarantee now that you are realizing irreducible representations of the proper orthochronous Lorentz group, what happens to parity? Parity is still given by the same formula. There's nothing changes here, except that now passing to the Weyl representation, which you want to see the explicit split between two different copies of Weyl Spinors. In the Weyl representation, gamma 0 is off diagonal, as we have learned. And therefore, what happens here is that actually, these spinors phi and chi, they now flip. So they flip under parity. So that's why sometimes the spinors called chiral, and chiral in Greek means a hand. And sometimes people call them left-handed and the right-handed. And what we learned from this exercise, that left-handed and right-handed spinors, while transforming completely independently and irreducibly under proper orthochronous Lorentz transformations, they actually turn into one another under parity. So they exchange under parity. So what was left-handed goes to the right-handed. What was right-handed spinor goes to the left-handed spinor. Although under proper orthochronous transformations, they transform independently. That is very interesting. So with respect, this shows also that to describe the full Lorentz group, you actually need both spinors, both copies of Weyl spinors. You need phi and you need chi, because with respect to the full Lorentz group, you also need to realize parity. And you know that you cannot restrict yourself just to the left-handed spinors or to the right-handed spinors, because then under parity, what was left-handed turns into right-handed. What was right-handed turns into left-handed. Next thing, which I allow myself also to quickly say today, is the following. If you look now at the Dirac equation from the point of view of phi and chi, you will see the following. The Dirac equation will take the following form if you substitute in this equation this split phi and chi and go to the Weyl representation for gamma matrices and compute explicitly what you get, then you get the following: d phi over dt minus sigma I d phi over dt, or over dxi, sorry. This is how Dirac equation would look like, plus I mc over h bar chi is equal to 0. This is one two-component equation, and the other two-component equation will involve derivative of chi. d chi over dt plus sigma I d chi over dxi plus I mc over h bar psi equals chi equals to no. Here was chi, and here must be psi. Right. Is equal to 0. This is how Dirac equation looks like. Dirac equation looks in the when written in the components of the Weyl spinors. This is how it looks like. And you see that in fact these are coupled equations. So equation for phi contains chi, and equation for chi contains phi. So equations are coupled. But there is one case when they actually decoupled from each other and become independent. And this is a case when mass of your particle is 0. Because when mass is 0, you see explicitly from this construction, then what happens is that this term disappears and this term disappears, and the equation becomes independent. And this equation for these equations for massless particle, they are called Weyl equations. So Dirac equations turn into Weyl equations, in this case of vanishing mass. So Weyl equations.
So can we say neutrinos follow Weyl equations?
Sorry, can we say?
That neutrinos follow Weyl equations?
Yeah, to a certain up to a certain amount, we can say that neutrino follows Weyl equation, but you know also that recent findings finding a neutrino mass.
Yes.
So you should be a bit careful with this.
Professor.
But yes, what you see is that in the case of vanishing mass, then your spinors satisfy separate Weyl equations. There is no coupling between spinors, but of course one equation turns into the other under parity. Under parity. In any case, each of these equations independently describe a spinor of a definite chirality. So you can say either left-handed spinor or right-handed spinor. So you get separate equations for left-handed and right-handed spinors. Of course, as I said, in the case if they are massless. And the mass term, as you see, leads to the mixing of these two spinors. So you cannot really actually, I mean, dynamically, they do interact with each other through this mass term. Okay, so Weyl equation is covariant with respect to the proper synchronous-Lorentz transformation, but as is clear, is not invariant under parity. And in fact, parity, what it does, as you see, it will transform this minus into this plus. Even in the massless case, minus will go to the plus. Yeah.
But for proper understanding of this parity transformation on Xi, so shouldn't we multiply time operator also? So as to combine these both things.
Yeah, we can also include time operator in the game, so time reversal operation in the game. Of course, yes, sure, you can include it. But for me, it's already enough to see what happens under parity. Sure, you can also consider what happens in the Dirac representation, what happens in the Weyl representation. Under this parity transformation, you can, but Weyl transformation, I think, what I'm saying, time reversal is not very illuminative in this case, because as you have seen today, the action of the T of this operation T on our spinor psi on X is given by T psi conjugate, and T is explicitly I gamma 1 gamma 3. That's what we have found, psi star. But these matrices are the same, right? They are the same. Are the same in Weyl, in Dirac and Weyl representation. In Dirac and Weyl. So from this point of view, and they are both off diagonal, and so their product is diagonal. So under time reversal, nothing bad happens. Spinors phi and chi continue to transform independently. But under parity, parity is important. Under parity, they do mix, or they do interchange. So from this point of view, time reversal is not showing you much. but parity shows you a lot.
Yeah.
Okay? That is how
Yeah.
it works. That is how it works. Okay, so in principle, this story about Weyl Spinors I told you completely. So let me see. So we are left with 2 lectures, December 5 and then December 13, as far as I understand. And I will tell you in these 2 lectures how to solve the Dirac equation, how to find and classify solutions, and then charge conjugation and antiparticles. This is our plan then till the end of the course. And if time permits, I will start talking about quantization, but probably this will go to the next semester. I don't want to rush too much. I want that this ground knowledge on the Dirac equation will be explained very thoroughly. Okay, then I think I have finished for today. So if you have questions, please go ahead.
Thank you, Professor. I have a question about we found out that the spinor representation of the Lorentz group is reducible. But I wonder if one of these invariant subspaces where this Weyl spinor live, if this invariant subspace, one of them can be further split in 2 invariant subspaces.
No, this is not possible. Further split is not possible. You are asking about if this is possible further to obtain irreducible splitting, say, 2-dimensional Weyl spinor into 1-dimensional representations.
Yes. How we prove that? How we prove that it is not possible?
This is you can see that simply there is no any other operator which is not proportional to the identity and which would commute with all operators realizing the corresponding representation. So that's you can, I think, very easily find yourself. So what we have found is that Sn theta is realized on, say, 2-component spinor in the way that we have cosine theta over 2 multiplied with identity matrix plus what was that? Let me see, what was that? That was I sigma n sine theta over 2. Yeah, so this is one matrix realizing rotation and another matrix realizing arbitrary Lorentz boost. Is a matrix we have found today is either 1 cos var theta plus minus, so you need to choose a sign plus or minus. No, suppose we choose plus, does not matter. Suppose we choose plus, and then sigma n sinh var theta over 2. So the statement is that you will not find any non-trivial 2x2 matrix which would commute with Sn theta and simultaneously with Sn var theta. There is no such a matrix. Statement is no such A, B, C, D 2x2 matrix exists except, of course, trivial one, identity 0, 0, identity multiplied by with a constant. Then it would mean that this representation is irreducible. according to the definition 2 of irreducibility I mentioned today. That's, of course, you can easily find yourself that this is not possible.
Okay, thank you. It's clear. And my last question, Professor, is about time.
You see, just maybe one more comment. You see that this equation eventually reduced to the following. You need to find a 2x2 matrix, which simultaneously commutes with all Pauli sigma matrices. Except identity, you don't have any other matrix which does this. No matrices, except trivial, except C multiplied by identity exists. Yeah, you see it from here. So essentially, identity is not important. It's will be because A, B, C, D will commutes with this one. So one in both cases is important. Then in the other, since n is arbitrary, at the end it reduces to commuting with all sigma i's. I is equal 1, 2, 3. But then you can easily establish that this is possible only if your matrix ABCD is just identity, essentially identity. So representation is truly irreducible.
Okay.
Mm-hmm.
Perfect. And Professor, the last question is about this time reversal. The operator we found out. We found this T and conjugation, and this matrix T. But you use the Dirac representation, and you said that is the same for Dirac and Weyl. But if we use another representation, how this matrix is independent of the representation or not?
I mean, of course, how the concrete operation acts depends on the representation. It does depend on representation, but the properties, the basic properties of the corresponding operation is not. It is independent of that. So, for instance, such issues like, for instance, we are discussing here, reducibility versus irreducibility should not depend on the choice of our gamma matrices. But you see, if you change gamma matrices from one basis to another, then you should consistently change them everywhere. You cannot say that I'm changing my, so for instance, I can say that I use Dirac equation to describe Lorentz transformations, but I use Weyl representation to describe action of parity or time reversal. This is inconsistent. This is not possible. You have to fix, if you want to work with a concrete representation, you have to fix it once forever for all the things which you are using in your theory. For instance, you can use the same representation in the Dirac equation, the same representation to describe Lorentz transformation, the same representation to describe parity and time reversal. Otherwise, you will have trouble. Concerning say time reversal, of course, if you will be changing representation, you might change the concrete way how this operation acts on the components of a spinor, but you will not change, you never change the nature of this operation as described as anti-linear, anti-unitary operation. You see? For instance, this is being anti-linear, anti-unitary is invariant property which you cannot escape, which will come back all the time, whatever representation you use. The same is with reducibility. If representation is reducible, it will be reducible in any representation of gamma matrices you use. So these invariant properties and invariant description of the operations which we are using, they are invariant in a sense that they do not depend, they are not related to a concrete representation of gamma matrices which we are using. Okay, I mean, we will see it next time, one more very clearly on the example of the charge conjugation operation, which connects particles and antiparticles. We will see it very clearly. That concrete representation of how it acts does depend on which gamma matrices you choose. But the basic properties, they are independent of that. Yeah. So in fact, all the properties in the theory are always defined up to what we call unitary equivalence. So theories which are related by unitary transformation, so in particular representations, unitary transformations of Clifford algebra, lead to completely equivalent theories. Yeah.
For the Weyl representation also, it follows the same Clifford algebra, right?
For Weyl representations, the algebra is what you mentioned about the algebra.
It follows the same Clifford algebra, right?
Yes, absolutely. Yeah, that's the point. So these gamma matrices, which are introduced as Weyl matrices or matrices in the Weyl representation, they do satisfy, of course, the same, absolutely the same Clifford algebra. Where they are? Here they are. These matrices satisfy the same Clifford algebra as these ones. Yeah, they both satisfy, these two sets satisfy the same Clifford. The same Clifford. And I said that there is this Pauli theorem, or Pauli lemma, as people call it, that any two different representations of the Clifford algebra in 4 dimensions, they must be related by unitary transformation. And indeed, this unitary transformation is here, which relates two sets of gamma matrices, and they both realize the same Clifford algebra.
Yeah.
Yeah, you can check it very explicitly. Unitary transformation cannot destroy neither Clifford algebra nor the hermeticity property of gamma matrices. You clearly see it from the construction of this algebra. Gamma mu plus gamma mu is equal to twice eta mu multiplied with an identity matrix. Multiplied with an identity matrix. So if I multiply it with u gamma mu, and then I write as u minus 1, u gamma nu, u minus 1, plus u gamma nu, u minus 1, u gamma mu, u minus 1. And on the right-hand side, you see that because I have an identity, that multiplication with u and u minus 1 does not change anything. I get 2 eta mu multiply with identity. And so these matrices, which are transformed by unitary transformation, they again satisfy Clifford algebra. If you call them gamma nu prime, then they satisfy absolutely the same relation. Gamma mu prime is equal to twice eta mu with the same metric. You see? And if the transformation is unitary, then I'm not changing the hermeticity property of these gammas. They have the same hermeticity property and there's the same Clifford algebra.
And
so I have a question. Yeah, maybe just continue your discussion and I ask later, maybe.
No, it's go ahead.
So my question is about actually from Dirac representation to Weyl representation, we actually changed the representation of Clifford algebra, and we got corresponding different representation of the Lorentz group, and those.
But they are unitary equivalent, because there is a unitary operator. That's exactly this unitary matrix U here. Where was it? It is this matrix, which tells you that this two different representations of the Clifford algebra, and therefore two different representations of the Lorentz group are fully equivalent.
Yes. What I want to ask is that if we consider, not in this case, but in some other theory, maybe if the representation between we transform one representation of Clifford algebra to another, but not by unitary transformation. What about the representation of group? Because here, I think in the previous lecture we said that all the different representation of Clifford algebra are...
Yes. No, for that you need to go to other dimensions. Then you, I mean, in 4 dimensions this is not possible, but in other dimensions it is possible. So you need to go to other dimensions in order to see this effect. And then you might have different non-equivalent representations of the Lorentz group, because there could be different representations of the Clifford algebra. And so in a way, you can have, in this case, you can say that you have, in a way, non-equivalent Dirac equations.
Yes,
you can have kind of a species.
So here in our case, the different representation of group are equivalent.
They are all equivalent,
Just because in 4 dimension, all the representation of algebra are equivalent.
Yeah.
Okay.
Exactly.
Okay, thank you.
So if you consider unitary transformations as equivalents, then you can say that there is only one non-trivial representation. You can take either Dirac or Weyl. All the others will be unitary equivalent to it. And so in this case, there is only one non-trivial representation of the Lorentz group, and all the others are just unitary equivalent to it.
Yes, I see. Thank you.
Professor, one question that how we saw this, that we only have 2 representations. Why we don't have any other type of representation?
That's because we are in 2 that's because we are in 4 dimensions. That's because we are in 4 dimensions, and we are describing basically particles with spin 1/2. If you would like to describe particles with spin 3/2, then you have a more complicated story. Because all what we have seen here is spinors either 1, 2, 0 in the description of the Lorentz group, or 0, 1, 2, 0, 1/2, either this spinor or this spinor. If you go to either high spin or another dimension, then you will have more complicated representations of the Lorentz group appearing. You should expect more complicated representations to appear.
So I didn't understand this this notation, 1/2 what does this mean?
It means that any representation of the Lorentz group is described by 2 half integers. So you give me 2 half integers, and I'll show you, and I'll exhibit for you a representation of the Lorentz group. So I need 2 half integers to specify it completely. So even in 4 dimensions, there are 2 such representations. One of them is dotted and another is undotted, and they are not equivalent.
What is this 0 showing? 0.
Just 0. Because there will be other representations. For instance, 1/2, 1/2, 1/2, 3/2.
Okay.
Yeah, you see, more complicated representations, which are characterized. And this, what we are having here, is the simplest one. So there is so the simplest representation would be representation 0, 0, but this representation is a scalar. And this is a scalar of the Lorentz group. Scalar. Then the next complexity is a representation of spin 1/2, 0. or 0, 1/2. Then there will be more complicated representations. Say spin 1/2, 1/2, 1,0, 0,1, and so on. There is an infinite chain of these representations parameterized by two half-integer numbers. But you should not be surprised that the two numbers do appear. Are you surprised that two numbers are needed to specify representation?
Yeah,
Know that?
this is notation type.
That's because this is not rotation group, which you probably acquainted very well, where you say having one half-integer is enough to construct an irreducible representation. For SL2C, there are non-equivalent representations, say, and this is clear. The difference between, in a sense, between these representations is clear in the following sense. I'll tell you. Maybe I'll tell you somewhere here. Informally, if you have SU2, you can think about this as universal cover of the rotation group. So let's talk about this SU2 as being just like representing rotation group in the form of the universal cover. Then you understand that SU2 acts on two component, has a representation in terms of 2 by 2 matrices, which acts on two numbers, Z1, Z2, okay? Now you can ask yourself, if you have a representation, so this means that any group element is a matrix, rho depending on G, where G is SU2 element, and this is 2 by 2 matrix. And 2 by 2 matrix acts on Z1, Z2, and gives you another Z1 prime, Z2 prime. Okay? And you know that this the fact that you are dealing with representation means that representation is a group homomorphism. So if you take a product of two elements, then you get rho on G1 multiplied by rho on G2. Okay? That is what means a group representation. Group representation is a homomorphism of the group into automorphisms of the linear space. In this case, it's two-dimensional space parameterized by this coordinate Z1, Z2. Now, if you have such a thing, what you can do also, you can just take these matrices rho and complex conjugate them. And you still get representation like this, yeah? Because this property still will be satisfied. I mean, in the simplest case of SU2, you can forget about the letter rho, and in the simplest situation, you can just talk about the matrices. So you can take G1, G2 acting on such a vector, and then it's clear that if you conjugate them, but this is still will be an SU2 matrix, and SU2 matrix acts on Z1, Z2. And then you can ask yourself, well, when you conjugate your matrices, you in fact construct another representation. Because in general, rho is not equal to rho star. These are two different representations. And the interesting feature of SU2 appears that rho star actually is not a new representation, but it's a representation which is unitary equivalent to the original one. There is a unitary transformation which transforms original 2 by 2 matrices into a complex conjugate matrices. And if you think about it, you can find what this matrix U is. It's a good exercise, actually, to show that such a transformation does exist. It will show you that the complex conjugate representation is actually not a new representation, but a representation which is unitary equivalent to the previous one. But for SL2C, which is a universal cover of SO13, this is not the case. If you do the same conjugation operation on SL2C matrices, then you can show that there is no such a unitary transformation which transforms the conjugate representation into the original one. They are really different. That's something which distinguishes, that is an important property, which is distinguishes SU2 from SL2C. Because in SU2, what distinguishes between SL2C and SSU2 is an additional condition. So matrices of SL2C, which are unitary, which satisfies this relation, U dega is equal to U dega U is equal to 1. They are called unitary, and this condition U dega or G dega, if you wish, G dega is equal to 1. This condition, in fact, what it tells you that G star transpose is equal to 1, which tells you, in fact, that matrices G star are related to the G minus 1 transpose by means of this property, extra property, which you don't have in SL2C. And so complex conjugate matrices can be expressed via inverse matrices transposed. And then you can use this property to actually prove that for SU2, complex conjugate representation is unitary equivalent to the original representation. And this is not the case for SL2C. And so SL2C, it's a Lorentz group. It's a Lorentz group. It's a universal cover of the Lorentz group SO plus 1, 3, and this is a universal cover of the rotation group. And then you see essential difference between them. Representations of the Lorentz group are much richer in structure. Much richer in structure in the sense that complex conjugate representation is not equivalent to the original representation, while it is the case for the case of the Lorentz group, for the case of the rotation group, sorry. Okay?
Yeah. Mm.
Another way to say, now I'm saying something which is not strictly true mathematical, and I have to excuse myself for that, but I write it roughly, just to give you an idea that SL2C, if you think about it, so what is this? These are 2x2 matrices of complex numbers with a unit determinant. Let's count the degrees of freedom. So A, B, C, D. You have 4 complex numbers, so in other words, 8 real. But then you have a determinant, and determinant gives 2 conditions on a real and imaginary part. So altogether, therefore, the number of degrees of freedom which you describe by SL2C is 6. 8 minus 2 is 6. So 6 real degrees of freedom. And of course, you understand that from the point of view of Lorentz transformations, these 6 degrees of freedom correspond to 3 rotations and 3 Lorentz boosts, right? Dimension of SU2 is 3, because it's related to rotations, and we know that due to the unitarity condition, we have further reduction of 6 degrees of freedom to 3. And in fact, if you think about this, then the Lorentz group is simply something like SU2 plus I, imaginary unit, multiplied by another copy of SU2. Here is 3 degrees of freedom, and here is another 3 degrees of freedom related to Lorentz boosts. And now, maybe from this representation becomes clear that since representation of SU2 corresponding to rotations, you represent, you parameterize by one number, half integer number G1, there should be also another half integer number G2 related to another copy of SU2. Again, because of this I is a bit non-trivial, because that's what makes this part non-compact and not to be a subgroup. But in any case, you see that in a way, you need another half integer number to describe the full variety of representations of this SL2C. Okay, maybe this analogy somehow will help you to.
Yeah, that's why we need two representations.
You need two
J1 and
numbers.
J2.
You need two
Yes.
half integer numbers to describe all variety of possible representations. You simply have more complicated group which contains rotations only as a subgroup.
So if like we had any third component, so we will had three elements to describe them. Represent.
Yeah. In general, the irreducible representations of the Lorentz group are parameterized by the values of the so-called Casimir operators. For rotation group, there is only one Casimir operator, but for the Lorentz group, there are two Casimir operators. Essentially, this is what is needed in order to specify its representations at the end of the day. And that's why there appears two numbers, J1 and J2.
Yes. So like for three particles, so it will be like follow SL3C.
No. Once again, so what I'm saying here is a very, very mathematical, not so rigorous statement. So you have to be careful. You have to be careful.
Yeah.
But every time you want to go to describe your own group, you have to figure out indeed the number of irreducible, the number of Casimir operators. Casimir operators, these are operators, well, it brings me a bit out of the present context. I should talk about universal enveloping algebra, and then in the universal enveloping algebra, there are operators which commute with any operator representing a group element, and in irreducible representations, Casimir operators must be proportional to numbers, because you are talking about irreducible representations. And so representations are characterized by the value of these Casimir operators, and depending on how many of them you have, you will get different quantum numbers, so to speak, which characterize your irreducible representation. So going to higher SL, yes, indeed, then you have more rich representation theory. But high SL are not related to Lorentz group. So for Lorentz group, we need only SL2C.
Yeah.
Which is the same thing, essentially, up to this issue of universal covering as SO plus 1,3, as proper synchronous Lorentz transformations.
I think related to this, you have some weight chart, right? A graph is like triangle.
Yeah, no,
SL
you see,
pentagon,
the simple thing is that now you just describe more complicated objects which transform under Lorentz transformations. You can have scalar, yeah? Now I told you about spinor. Spinor can be dotted, it can be undotted, with dotted and undotted. But then you can describe more complicated objects. You can describe, for instance, a spinor which also carries a vector index. It could be vector representation. So how you would describe a spin 1/2 particle? You need a vector index, particle of spin 3/2, and a spinor index. And you may have this object and you may have this object here. You see, that's why these numbers do appear. integers and half integers. You can have tensors which have any number of indices undotted, alpha 1 and alpha n, and dotted indices, alpha dot 1 and so on, alpha dot m. Such an object, tensors made out of these indices. That's exactly where these numbers do appear. So now to describe this, you need half integer specifying n components of dotted spinors and m components of undotted spinors. And you can make under imposition of some conditions of symmetry on these alphas and alpha dots, you will describe irreducible representations. And in this respect, that's exactly those which will be characterized by these two half integers numbers, J1 and J2. Say spinor which has a certain number, which is a tensor with respect to the indices alpha and this indices alpha dot. Like in the normal world, you have vector, but then you have, say, G mu nu, or you can have something which contains 3 indices, mu nu lambda, and so on. Higher spin, but here spin, because of nature of the Lorentz group, you have indices which are not only undotted, but also dotted. And these are not equivalent. You cannot describe them as the one and the same thing. You have to distinguish them. So you can have spinors which have a certain number of undotted indices and a certain number of dotted indices. And that's exactly the origin of these two numbers, J1 and J2, which would describe such objects as irreducible representations of SL2C.
Yeah, makes sense. Yes. I think
Yeah.
related to that, you have some like Clebsch-Gordon coefficients also, right?
No, in a way, you can build up representations of higher spin by taking tensor products of representations of lower spin. So in this respect, yes, you can think about decomposition of the tensor product of representations into irreducible ones. Just like, you know, the rule when you multiply representations of the rotation group of spin 1/2, right? You know this rule. If you take representation of spin 1/2 and tensor it with another representation of spin 1/2, then this is reducible representation, and it will be decomposed into irreducible components of spin 0 and spin 1. Yeah, you know this rule for SL2C, J1 minus J2. Where J is changing from J1 minus J2 up to J1 plus J2. Yeah, you know this. You know this rule. So for the case of 1/2, you have 1/2, 1/2. So you get spin 0 and spin 1. And the same thing, you can play the same game also with Lorentz group. But for the Lorentz group, you will get a certain number of undotted guys. Say, for instance, you can ask yourself, so what happens if I multiply two undotted spinors like this? How I decompose them over irreducible representations? Or you can have more complicated story. You can have here 1/2, 1/2, and here 1/2, 0. Or you can here 1/2, 0, and here 0, 1/2, like this, and so on. And then you will be constructing decomposition over irreducible representations, and eventually in this decomposition, all representations with two half integer numbers, J1, J2 appear.
Yes, yeah. Yes.
And Clebsch-Gordon coefficients, this will be coefficients arising in this tensor product decomposition. They will describe intertwining operators which intertwine reducible representations with its irreducible components appearing in this decomposition.
Yes, you're right. Okay, sir. Thank you, sir, for the explanation.
Okay, my pleasure. Okay, then if you don't have any further questions, we will hear each other in 1 week, and we will talk about explicit solutions of the Dirac equations in terms of so-called plane waves, and then also about charge conjugation, particles and antiparticles. Otherwise, I wish you a pleasant day, and bye-bye.